All right. In this video here, we're gonna talk through example one on the chapter 10 example worksheet, which dealt with determining whether giving a name as a part of a greeting meant increased tips for a waitress at a Sunday brunch in a restaurant in Southern California. Right, so this was reported by Garrity and Degelman in 1990, where a waitress used a random mechanism to determine whether to give her name as a part of a greeting, and then she kept track of how much the party tipped at the end of their meal. So she picked out a sample of 20 parties to whom the waitress gave her name, right, and 20 parties to whom the waitress did not give her name. And for the 20 parties whom the waitress gave her name, the tip was 5.44. That was the mean tip with a standard deviation of 1.75. And for the parties whom the waitress did not give her name, the sample mean was 3.49 and the sample standard deviation was 1.13. So we're going to use this example here to answer a few questions. All right, so the first one asks us to identify the explanatory and the response variable here. So the response variable in this case is going to be the amount of tips she received, and the explanatory or the predictor variable is whether the waitress included her name as a part of the greeting. Right, so the response, which is the amount of tip, is going to be a quantitative variable because we have a measurement here, and the explanatory is a qualitative. Right, so this is also a binary variable, something called a binary, because there's two options here. This is a yes, no, right? So the waitress either included her name as a part of the greeting or did not include it. So this is a binary variable. So this is a qualitative one. So now the waitress was trying to determine whether giving her name to the customers increased her tip or not. Right, so what we would like to do is we'd like to test this hypothesis, which means we're going to need to come up with a null hypothesis and an alternative hypothesis. The null hypothesis is going to be that the population mean for when she gives her name, for mean tip, is going to be the same as when she does not give her name. Or in words, the population mean tip will be the same, regardless of whether she uses her name or not at the start as a part of her greeting. And the alternative hypothesis, which she's trying to find evidence for, is that the mean tip actually increases when she uses her name as a part of a greeting than when she does not. So the mu name is larger than the population mean when she does not give her name. So the alternative hypothesis is that the population mean tip amount is greater when she gives her name as a part of a greeting than when she does not. All right, so now that we have stated our alternative and null hypotheses, the question C asks us what a type 1 and type 2 error in this study would mean. And would you consider one of these errors to be more serious than the other one? So let's see, what is a type 1 error? Well, type 1 error is when we reject the null hypothesis when it is actually true. All right, so in this case here, it would be, type 1 error would be deciding her name is helpful, giving her name is helpful when it does not help. And the type 2 error in this case is going to be deciding using her name is not helpful when it actually is. So those are the type 1 and type 2 error in this study here. So the question is, based on this study, is there one particular error that is more harmful than the other? Well, clearly, right? Type 2 error in this is more serious because even though giving her name when it might not help requires very little effort, deciding to not give her name when it actually helps is going to be very detrimental, as she's going to lose out on tips. Right? So in this particular example here, the type 2 error is clearly more serious because you end up losing out on tips as opposed to the extra effort of just giving your name even if it would not help. All right, so now that we have stated the null and alternative hypotheses, we would like to go ahead and compute the test statistic. All right, so when we are computing the test statistic, we need to identify the type of test we are using. So is this a non-pooled t-test? Is this a matched pair? Or is this a one population mean? Well, clearly we are comparing means across two populations. So one population was where she did not give her name as a part of a greeting, and the other population was when she did give her name as part of a greeting. So we're looking at two means, and now the question is, are these data paired here? The answer is no, they're independent from one another. All right, so which means we're going to be using a non-pooled t-test here. T, because the population standard deviation is not known. The only thing we know is the sample standard deviation, and the sample standard deviation, we are going to use that to so in this case here, we're going to be using a t-test. So if we're doing a t-test, we need to figure out two things, the t-score and the degrees of freedom. Well, the t is going to be the difference in the sample means divided by this quantity here, which is the sample standard deviation of one of them squared divided by the sample size plus the sample standard deviation of the other squared divided by the sample size. And when we do the computation here, we get the t-value is 4.19. And then we're going to go ahead and compute the degree of freedom using the formula for the non-matched non-pooled t-test here, and we get that the degree of freedom comes out to be 32.50, which means we're going to round down here. So our test statistic is 4.19, and our degree of freedom is 3250, which we're going to round down to 32. So then we're going to go ahead and find the p-value by looking at the table. And remember, the table for t-values are limited. All right, so in this case, when we're looking at degree of freedom 32, we realize that for t-value 2.738, the area to the right of 2.738 is going to be 0.005. So if we're looking at our test statistic, which is 4.19, we realize that the area to the right of 4.19 has to be less than 0.005. Okay, because 4.19 is 2.738. Again, this is a rough approximation using the limited t-table that we have. However, what we can say is in this case, the p-value is going to be less than 0.005. Right? We are looking at a right-tailed, so we're looking at the area to the right of our test statistic, which is 4.19, and based on the table, we can say it is less than 0.005. However, if we were to use StatCrunch, and I'll let you do that on your own, you can verify that using StatCrunch, the p-value in this particular example is going to be 0.0001. So the next question is, if you found your p-value, which is 0.0001, what test decision would you reach at significance level 0.05? So, and again, what does this decision mean in the context of this study here? So remember, if we want to make our decision, we're going to have to compare the p-value with our significance level. So in this case here, the p-value is smaller than our significance level, which means we're going to reject H0 and we're going to accept HA. Right? So we're going to reject the null hypotheses and accept the alternative hypotheses. So in the context of this example, what that means is that the data provides enough evidence that the waitress giving her name to the customers does in fact lead to higher tips on average. Right? So this is, the p-value is 0.0001, which is a small probability. Right? So there is a strong evidence here for us to reject null hypotheses in favor of the alternative hypotheses. All right, so that's the decision here. However, remember, we are running a non-pooled t-test here, right? So when we're running a non-pooled t-test, there's a bunch of assumptions, technical conditions it should satisfy before we run this test here. And those conditions are, well, our sample needs to be simple. So we should have simple random samples. We should have independent samples, and either we should have a normal population or large samples. So the question is, did we have enough information to check whether the technical condition of the two samples, the non-pooled t-test, are satisfied? So clearly there's not enough information. First, we are not sure if the sample is in fact random. we don't know is the waitress deciding to give her name and not give her name randomly. Or in other words, we don't know once she gives her name if she's giving the same service to both the party that she gave her name to as well as the party that she did not give her name to. All right, so that's first. The second one is that, well, we don't know whether the population is normal or not, and the samples are not large enough, right? So the samples are less than 30, so we need bigger than 30 for it to be large. So in this case, we don't have large sample sizes, and we don't have individual statistics either. All we have is the summary stats. So we can't go ahead and check whether the data would indicate that the population is approximately normal by looking at the probability plot, because we don't have the individual data here. We only have summary stats. So if we could request some additional information from the waitress, what we would ask the waitress for is we would ask the waitress to provide the tips that she received from each party. Right? So we would need the individual tips, and then what we could do is we could look at the probability plot for the individual tips, and if the normal probability plot was somewhat linear, we could say with some amount of confidence that the data the population is coming from is approximately normal. But in this case here, since the sample sizes are not large and we only have summary stats, the technical conditions for the test are not satisfied. Right? So now what we're going to do is we are going to plug along as if the technical conditions are indeed satisfied, and we're going to compute the 95% confidence interval for the difference in population mean tip amounts between when the waitress gave her name as opposed to did not give her name. And we're going to interpret what that interval means in this context here. All right, so remember we already computed the degree of freedom, and now in this case, since we're looking at 95% confidence interval, our alpha is 0.05, so we need to find T alpha over 2. When we go to the table, we see that our T alpha over 2 is 2.037. Once we know our T alpha, we know our 2 sample means, we know our 2 sample standard deviation, so the formula right here gives us the endpoints of the confidence interval here. So when I plug in the corresponding values and I put it in my calculator, I get that the 95% confidence interval is from 1.001 to 2.899. So what this means is we are 95% confident that the waitress would get between $1 and $2.9 more tip per party if she used her name. Right, so that's what that means. So we're 95% confident that the waitress would get between $1 and $2.90 more tip per party by giving her name. All right. So finally, regardless of whether the technical conditions are met, and unfortunately, as we said earlier, they're not, we're going to summarize our conclusions. So the first one is that we realized that the p-value was 0.001 earlier, which meant that the data provided strong evidence that the group that the waitress gave her name to gave her significantly higher tips. All right. So again, as we mentioned, there might be other factors that come into play. For instance, she might have given better service to the party who she gave her name to subconsciously, as opposed to the parties that she did not give name to. But unless other factors come into play, there's a strong evidence to suggest that the group that the waitress gave her name to gave her significantly higher tips. Also, the 95% confident interval tells us not only did she get more tip, but in fact, the increase in tip was actually quite significant, right? So she got on average from $1 to $2.90 more per party when she used her name. So that's quite a significant increase. Right, so that's how we do hypothesis testing and confidence intervals for non-pooled T intervals.